All right, we are talking today about chapter 10. We are going to be looking at 10.1, 10.2, and 10.3. The bulk of that material is going to be here in 10.1. So this is a long section. The other two are a little shorter. All of it very important. And, there's no shortcuts to just plowing through it. So that's where we are. Today we're talking about, in 10.1, angles and right triangles, angles and right triangles. And we, trying to get my slides to go, are going to practice converting angles between decimal degrees and degrees and minutes. We briefly talked about the idea of an angle being able to be expressed in degrees and minutes in the last class. So we'll talk our previous class, not last one, but previously. So we will look at that a little harder, convert angles between degree measures and what we call radians. Radian measure, different way to talk about the size of an angle. We will talk about arc length, area of a sector. None of that necessarily has to mean much to you right now. We'll get there. And calculate both linear and angular speed, and talk about special right triangles. There are special right triangles that we'll look at. So there's a lot in this section. We start, though, I have the first slide here actually preparing you for something that shows up in the homework that is not directly part of the 10.1 slides. And so I put it in here to help you with that homework problem, number 24 and 10.1. It really is sort of a reboot of some ideas we saw in previous classes concerning relationships among angles. So it's review somewhat, but again, it's not directly addressed. It shows up in the 10.1 homework, but it's not in the 10.1 notes and slides. So therefore, we're going to take a look and review. So the goal here is to look at that crazy looking diagram and find X, Y, and Z. Find X, Y, and Z. So how would we do that? Well, we might start with the fact that there is one angle in here that we do know. Right there, right? There's one angle given, one, which is 90 degrees right there. So we know something about the fact that 2/3 of some X value that we don't know and 4/3 of that X value that we don't know, plus that 90, all of that sitting here on a 180-degree straight line. The total of those three would be equal to 180. So stop and make sure you're seeing that. So the total of the three angles, here, here, and here, 4/3 X plus 2/3 X plus the 90, the total of that has to be 180. So that gives me a way to start solving for this. And from here, it's actually kind of downhill because if I can, sorry, I'm trying to make that look nicer and I made it worse. If I can, that didn't help either. Trying to make it not look like a 9. Hold on, let me try one more time. Okay, if I can find X, I can certainly get to the others as well. I would be able to get to the others as well. So what are we going to do? We can subtract the 90 from both sides as a start. And I can recognize that 4 plus 2, 6/3, 6/3 is just 2. So actually, very quickly come down to something that's pretty easy to simplify. And I can say, whatever else is going on, that X has to be 45. From there, what could I do? Well, all I really need to do then is take that 45 into, for example, 4/3 times the 45, substituting in the 45 for the x and do my solving there. This is going to end up being 60. 4/3 of x is 60 degrees. From there, I actually could get everything else in the circle, or I'm sorry, in the diagram. I could get everything else in here by way of my knowledge of opposite angles and by way of my understanding that the 60 plus the 90 plus this angle here, that 60 plus the 90 plus that unknown angle right there, again, must equal 180. So from there, I believe that you would be able to easily reason your way through that. So I'll let you finish it, and you can finish it, and, you know, as you see it in the homework. But I want that to be clear. Make sure, again, that you ask in class if something is not clear, because this is a typical kind of question. You may see this again in some of your travels. All right, so we'll go ahead and clear that. I gave you everything you need to be able to confidently finish that. Converting angle units. In most practical work, angles are measured in degrees and fractions of a degree. Smaller units have been defined as follows. So we saw this in previous class, that we can take 1 degree and break it down into much smaller segments called minutes. And we say that 60 minutes is equal to 1 degree. And we even could go further than that and take minutes and break them down into 60 seconds. In most of your experience, this level of precision is not necessarily going to be something you'll see much of. Sometimes in your work, you'll need to convert an angle that is measured in decimal degrees, though, to its equivalent measure in degrees and minutes. In other words, you may be in some circumstances that require you to work as far as defining an angle in its minutes. So let's think about how we would do that. Converting a fraction of a degree to degrees and minutes. For example, somebody says to me, I have an angle that is 17.5 degrees, but I want to think of that in degrees and minutes. Well, the first thing to recognize is simply that the whole piece doesn't do anything. The 17 just sits there. What we're really concerned with is what to do with this 1/2 of a degree. We want to know what 1/2 of a degree is in minutes. That's the goal here. So the 17 just sits out here and waits for something to happen. But the 1/2 a degree, to convert to minutes, it's a unit multiplier, as I have been preaching. Unit multiplier. If I know that 60 minutes is equal to 1 degree, then I can certainly get away with writing a multiplier of 60 minutes over 1 degree, because this is a fraction that is equal to 1. And therefore, it's a fair unit multiplier, and it will allow me to get my conversion done, because we have degrees and degrees canceling. What remains is all the minutes. That's all I wanted. Now, you may have said, well, I saw this one coming. Why are we going through the rigmarole here? 60 over 2, 30 minutes. Clearly 1/2 a degree. If you recognize that a whole degree is 60 minutes, a 1/2 a degree has to be 30 minutes. But of course, this half business is not always going to be that simple and easy. It might be a fraction that's much harder to anticipate what those minutes are. So let's do one that's not quite as just obvious as that. And I'm going to just throw something in over here to the side. So suppose I had, for example, 5/8. of a degree, 5/8 of a degree. And I need to convert that to minutes. Again, my unit multiplier allows me to set this up so that the degrees will cancel. I want degrees on the bottom, so they'll cancel with those degrees up there in the top. 1 degree is equal to 60 minutes. So those are gone. And I am left looking at basically 300 there in the top, divided by the 8 in the bottom. Now this will not come out real tidily. It's not a whole number, that is. But I could safely say that 5/8 of a degree, and you should look at this in your calculators, 5/8 of a degree is 37.5 minutes, right? That's the conversion. So on the next slide, there's another to practice. Oh, we're going the other way. So what about if we have to go in the other direction? Here we are looking at 72 degrees and 6 minutes, and we're asked to convert this back to decimal form. We're kind of going the other way. How would that work? Well, once again, 72 degrees just sits around waiting for things to happen. But the real question is, what does that 6 minutes look like if I convert it back to degrees? That's really what we're trying to do. Convert it back to degrees, and it'll be some decimal 72 point something out here in the end. So how do I do that? Well, again, think hard about your unit multiplier. You've got minutes up here in the numerator. If we put some minutes down here, then I can engineer that cancellation. 60 minutes is equal to 1 degree. This is the unit multiplier equal to 1. Therefore, I will not go to math jail if I multiply my values by 1. Nothing changes except what I call it. But the size of that is not changed. So here, again, this is a cancellation. We set it up. We wanted it to happen. The minutes have canceled. I'm left with degrees. And again, the 72 is unchanged, waiting for something to happen. But over here, I have 6, basically 6 over 60. You can see that 6 over 60 is 1/10. So that 6 minutes, 6 over 60 is the 1/10. My units is the degrees sitting right there. So my conversion of 72 degrees 6 minutes to decimal form is that original form is equal to 72.1 or 72 and 1/10 of a degree. Okay, so if we are converting from partial, either decimal or fraction of a degree to degrees and minutes, we're multiplying that fraction of a degree by 60 minutes over 1 degree. If I'm going in the other direction, if I'm starting with degrees and minutes, and I'm trying to get to a decimal or a fraction of a degree, I'm going to multiply by 1 degree over 60 minutes. Of course, the two multipliers are the same relationship. It's just the order in which they're stated. And you always know which order to use if you think about what you're trying to get rid of. Here we were trying to get out of minutes, so we put minutes in the bottom. And, conversely on the other directions. Okay, so there is that. Slides to go. They don't always want to move the way as quickly as I ask them to. Scientific calculators have special keys designed for entering angles in degrees and minutes and for performing angle conversions. I am not especially thinking that this is something that is real critical that you learn to do right now on the calculator. So what I'm going to do is suggest to you that you just kind of remember that that information is there, and you will, no matter what happens, if you hang on to your notes after this class is done, you'll have this notes to refer to if you should ever want to, and you could, excuse me, come back and take a look at those directions if you needed that. It's not something that necessarily you need to learn to do on a calculator right now, but that information is there if you want it. Radians. In some scientific and technical work, angles are measured or described not by degrees, but by something we call a radian. A radian has this kind of definition. It comes from this idea. A radian is the angle at the center of a circle that corresponds to an arc length exactly one radius in length. So what that's saying is if I have some angle, and say I had a radius here, maybe it's equal to 4 units, whatever the units might be. And of course, that makes all of the radii the same. If I have a distance along the circumference of the circle that is also equal to 4 units, then the angle that created that 4 is 1 radian. That tells you, you can kind of see from the diagram as well, that a radian is large compared to a degree. A radian is about 57 degrees. There is a calculation and a definition here that will allow us to convert back and forth as we need to. A radian is equal to 180 degrees divided by pi. That's an alternative way to state, a definition of a radian. It's equivalent to this idea. You don't need to worry about that especially. But it is 180 over pi. In other words, if you think about well, we'll see it in practice. Just go ahead and show you the examples and usually see what's going on. So suppose, as I said, we use this idea, this relationship to convert back and forth between degrees and radians. And you will find that you have to do that, a good bit. So suppose I start with degrees. I'm looking at 43 degrees, and I need to get out of degrees into radians. So what am I going to do? I'm multiplying by whatever version of this would get me out of degrees and into radians. This pi is in radians. The relationship we see right here says the 180 degrees is the same as pi radians. I put the conversion in this order because I want my degrees to cancel with those degrees. I'm canceling degrees. I'm canceling those units using that unit multiplier because pi over 180 is a fraction equal to 1. It's fair to use. It's not going to send me to math jail. It's equal to 1. So my degrees are gone. I am able to say in a precise form, I can say that 43 degrees is equal to 43 pi over 180 radians. Now, something else that's a little odd to me about the radians is that we don't ever say that it's radians if there's no unit stating. In other words, I don't actually write this out. This is 43 pi over 180 radians. If there's nothing written here, it's radians. So I can't tell you why. I don't know. But it is true. So 43 pi over 180 is the exact form, or if we needed an approximation, we could do that in the calculator. 43 pi divided by 180 is about, so 0.75 radians. It's about 3/4 of a radian. Okay. 60 degrees. How do we convert that to radians? We multiply by pi over 180 because the 180 degrees will cancel that degree and that degree. So we say that this one is 60 pi over 180, but 60 and 180 have a common factor of 60. So this fraction, that fraction reduces, right? Divide top and bottom by 60. And so the exact form of this one, 60 degrees, is that is pi over 3 radians. And in most cases, we would leave it that way. As you do more trig work, you'll see, you know, that this is sort of a landmark type of an angle. It tells us some things. So we leave that in that exact form, pi over 3. 142 degrees, again, multiplied by pi over 180. The 180 goes in the bottom because I want those degree units to cancel. I get here 142 pi over 180. And again, either you might either think in terms of reducing the fraction there, because they're certainly both even numbers, if nothing else. So that's what, 71 over 90. Or depending on, you know, again, you have to look at your context and your directions, do what the context requires of you, or read your problem directions carefully. This would amount to, as an approximation, about 2.48 or 2.5 radians, roughly. This is the exact form. This is an approximation. Okay, so that is getting out of degrees and into radians. So as you might guess, we want to practice in the other direction as well. So how do we get out of radians and into degrees? 1.3 radians, and the context here, of course, if we just saw 1.3 sitting somewhere without any context, we wouldn't know it was radians. We wouldn't know what it was. So you do see that abbreviation mentioned here. But the deal with that, again, is to realize that in this definition, in this relationship, the pi figure, the pi value, essentially is a radian value. So I'm essentially trying, again, to cancel, and again, I'll write it this time just so that you see I'm saying that pi is a radian unit, that I'm going to cancel those units. I want the radians to cancel. So I'm putting the radians in the bottom, so they cancel with this radians that I have in the numerator. And I'm left with degrees, which is what I'm trying to get to. And therefore I have 1.3 times 180, so 234 over pi. That pi value is there. That's still there. That's a multiply or a constant. It's still there. So I have 234 over pi degrees here. Once again, if you need the approximation, you can always get that. 234 divided by pi in your calculator is approximately 74.5 degrees. Okay. This one, since we practiced several rounds now, I'll leave one for your practice. So we'll go ahead and grab this one as a in-class activity for day 12. And this will be number 1. So you'll take yourself through the same process there and convert from the radians to degrees. How much is 0.5 radians in degrees? All right. Sectors. A wedge-shaped portion of a circle is called a sector, otherwise known as a piece of pie, right? Or a piece of cake. It looks like that. It's that shape. If you think about the shape of a piece of pie, you're thinking about a sector. Both the area and the length of that arc out here, the length of this distance right there, can be expressed most directly using radian measure. So this is an example of where we start to actually bring in the radian unit. An arc length, that S distance, will be the radius times that angle right here when A is in radians. The area of that sector is 1/2 times the radius squared times the angle measure in radians. The sector formulas only work when the central angle A is in radians. And we don't actually, work with these in the other way at all. So again, we're into the radians, and we have to really get some buy-in and bear down and kind of live in that world for a while, because that's how all of our calculations are going to run for a bit. I've put back down there that arc length formula. I can't tell you why it's called S. I don't know, but I've identified it here for you as well. So we've got a sheet metal worker. He wants to know the arc length, S. He's trying to figure out this distance. This is that arc length that he's trying to figure out. He wants to figure out that arc length S, and then he also wants this area, all of that blue. He wants to know what that area is with a central angle of 150 degrees. It's been cut from a circular sheet of metal with radius 16 inches. You can see that specified on the diagram. So the radius, of course, that's okay, but the central angle of 150, we can't use it in that form. We have to get out of degrees and into radians. How do I do it? I use my unit multiplier. I want to get out of degrees, so I put degrees in the basement. I remember that 180 degrees is equal to pi radians. And at whatever stage, you can start to, work out these cancellations, simplifying this fraction. In other words, this is certainly going to reduce by 3. We can divide the top and bottom here by 3. So I have 5 pi over 6. 5 pi over 6. Now you'll find often that because we, we want to keep our precision as, tight as we can do without, a lot of difficulty. There's really no reason right here to convert that to some approximation. We're not really needing to do that right yet. We can work with it as it is. So my R value in this little story, the radius there is 16. And my central angle, the 150 degrees in radians, is 5 pi over 6. When I get that multiplication done, and you might say, well, there's some cancellation I could do up front. Yeah, whenever you want to see it, you can certainly do that. 16 and 6, in other words, have a common factor of 2. So I could go ahead and recognize that right off if I wanted to. Divide those both by 2. So I end up with 40 pi over 3 That is this distance, 40 pi over 3 inches. Whether or not from here you convert that to some approximation depends on the context and on your directions. So be careful as you're working out problems in MATLAB and eventually on the exam. Make sure that you're paying careful attention to directions. The approximation for this in your calculators, just if you want to kind of check it and see what it looks like, is close to 42 inches. Very close to 41.9 inches. Okay, so take a look carefully at your directions when it comes time to actually stating these values, whether you need the exact form, whether you need an approximation, if you need the approximation to how much rounding, you know, all of that. So look carefully for that. But that arc length is about 42 inches, 40 pi over 3 inches. So let's do the area then. He also wants to know that blue area. And so we substitute in. Area is 0.5 or 1/2 times. The radius was 16. 16 squared is 256. Let's check. And then the A, remember again that 150 degrees. 150 degrees, when we converted that, this was that cancellation. We had 15 pi over 18, top and bottom, the 15 over 18 reduced by a factor of 3. So this was 5 pi over 6, if you remember from the previous slide. So this is 5 pi over 6. That's the A. We've substituted that in. And so running that calculation, we get 0.5 times the 256 times 5 times pi, all of that. And what I'm doing, you can do what you think works and hope it's correct, but I'm going to get all of that numerator taken care of first and then divide by the 6. The approximation for this, the decimal approximation for this is 335, roughly 0.1. And again, my units are in inches. So this is square inches, is that area, about 335 square inches. If for some reason you needed the exact form of that, you could certainly get it. It would be, so that's 128 times 5. So the exact form, if you needed it, would be, again, all I'm doing is multiplying the 1/2 times the 256 times the 5 in the top. That's 640. So I have 640 pi over 6. That could be reduced by 2 everywhere. So 320 pi over 3. So that would be the exact value if you needed it. And again, look at your directions and, you know, be sure that you could produce either one as you needed it. All right, that's the area of a sector when the angle is given in terms of radians. Here's another interesting area of sector kind of question, and this one did come from some homework problem I saw. So I've tried to replicate that somewhat, change the numbers, but you'll see something like this in the homeworks. So this is a wiper. That's the wiper blade down there. And as you know, the wiper will move back and forth And we'll create, if you think about it, it's creating a certain arc length right there and a certain area that gets wiped clean of rain, hopefully. So the total arm and blade of this wiper is 14 inches. That's the whole thing. It rotates back and forth for an angle of 100 degrees. Right there, this is 100 degrees. The shaded region is the portion that's being cleaned by a 9-inch wiper blade. So be careful with that. Think about that. Doesn't that have to mean that this part, we don't really care. It doesn't have much to do with our story at all. And the part that matters, because this would be the radius measure, would be that 9 inches right here, this part. The blade itself is a 9-inch blade that's wiping that turquoise area. So we want to know the area of that region cleaned. And again, this has to be done in terms of radians. That 100 degrees converted to radians means I want the degrees in the bottom so that I force that cancellation. The pi radians in the top, that's gone. So the angle in radians, so I can divide both by 2 anyway. So I get 5 pi over 9. That's the angle in radians. 5 pi over 9. 100 degrees is 5 pi over 9 radians. So that area is going to be 0.5 times the r squared is 81 times the 5 pi over 9 radians. So again, depending on your context and your directions, you may be asked to give this in an exact form. You may be asked to give it as an approximation. The approximation for that looks like 636.2, so close to 636 square inches. If you wanted the exact form, just to show it to you, it would be, so 202.5 pi over 9, very lumpy looking. 202.5 times pi something's not great. All that again. All that. Maybe you're spotting. If you were doing this, you might realize what I missed. So keep an eye on it. If you think you have it straight and I don't, then you take a look here in a minute and see if you see what I'm seeing. So the problem here was what? Okay, so if you were here, I'd ask you, I failed to divide that by the 9, right? That's what happened there. So let's fix that. Did seem big. Doesn't make sense, 600 and some inches. So 70.7, that looks more reasonable, square inches. And again, the exact form of that is there if you would like to see that or needed it. Okay, so I have a feeling the application questions will mostly be asking you to give that approximation. I just think it's important, again, that you keep bearing down on the idea that this is only an approximation. It is only an approximation. And the exact form is right there. All right. If you have questions, let me know. email me, send me a question in the chat, not chat, but in the inbox out of Ivy Learn, whatever it takes. Here's another interesting one. I've given you there, next slide. I've given you some workspace because this is kind of a big one. So we've got outfield fencing for Little League field, and it forms, the fencing, of course, forms a circular sector with home plate as the center. A fence is placed at a uniform distance of 216 feet from home plate. This is the fence. Uniform distance of 216, they're telling us that this is a radius of a circle. Uniform means that we can count on the fact that it's the same in both spots, and therefore it qualifies to be the radius of a circle. The boundary of the fence, which extends partway into foul territory, creates an angle of 116 degrees with home plate. So we're told right there that this is 116 degrees. Here's where things get exciting. Topsoil has to be brought in to cover the sector to a depth of 2 inches. How many cubic yards of topsoil are needed? Wow, right? So let me see, I want to make myself a note so I can transfer that to the next page where there's no writing. Okay, so let's take that cleared and get where we have some space. All right. So again, the goal is topsoil at a depth of 2 inches across this entire area, which says, of course, we have to find that area first. But then we also want to calculate this in cubic yards. Cubic yards to a depth of 2 inches. All right, so how do we do that? Well, let's get this area under control first. So once again, these distances were 216 here, and this is a 116 degree angle. So let's work on getting that angle into radian measures. So 116 times, again, 180 degrees in the denominator so that I can force the degree units to go away. Because the only way I can use my area formula is if this thing is in radians, if that A is in radians. So I get 116 pi over 180. I could divide top and bottom by 2 anyway, and still have my precision in place. 58 pi over 90. And then I actually, now that, I'm looking at it, I can see I could divide again by 2. Both of those are even. So I'd have 29 pi. 29 pi over 45. That's as far as that would go. So that's that angle, 29 pi over 45. That area then would have to be 0.5 times the radius squared. So 216 squared. You get a big number, 46656. You should be doing this with me. That's the radius squared times the angle in radians, 29 pi over 45 is equal to. So given that this is clearly an application question, the approximation would be appropriate as long as we're pretty close to exact. So 0.5 times 46656 times 29 pi divided by 45. Isn't this fun? So we get approximately 47,229.4 watts. What is this? Well, remember that our units here were feet. So this area is square feet. This is square feet. 47,229 square feet. So, what I'm doing here, you can't see me, but I'm doing it, is because the numbers and the sort of the context and stuff, the numbers are large enough that it's not real familiar to me, and therefore it's not easy for me to judge whether or not this is reasonable. In general, though you can't see me doing it, every single time I ever write a calculation, I'm checking, and because that's what happened on that wiper one a few minutes ago. I'm checking to see if it's reasonable. And since this calculation in this context is, I'm not terribly familiar with the things of that size. Neither are you. And, to say, oh yeah, 47,000 seems about right. Most of us would not be able to say that. So I double check, and in other words, just to, since it's not familiar, to judge whether it's reasonable, I double check the calculation. So that's the thing, you should be doing that. Double check your calculation in the case of units that or circumstances just unfamiliar, or where you get really big numbers. It's hard to judge. Our experience doesn't extend that far unless you've done this sort of work. And so double check your calculation. What I'm doing here, besides writing it wrong, what I'm going to do here then is to consider the fact that, and given the context, I would say maybe we can dispense with that. It's an approximation, but this is a big field. It's not like 4/10 of a square foot is real meaningful in the context. So I'm going to go ahead and take the whole number, 47,229 square feet. Remember that we were asked to cover this in topsoil that is measured in cubic yards. So I have to get out of feet squared somehow into, at least in, I can't get from feet squared into cubic yards. Feet squared is flat, cubic is cube. But I could get into square yards, right? Feet squared. I can get out of feet squared and into yards squared. What would that look like? Think about so I want to get to yards squared. How are we doing that? So if I want a yard, 1 yard, 1 yard, that's my yard squared. Think about where my feet are. 3 feet this way, 3 feet this way. What that tells me is that there are 9 square feet inside 1 square yard. 9 square feet inside 1 square yard. Okay, let's get that much. So 47,229. And the reason I brought this out, it takes a while to get through this, but it is in your homework. One like this is in the homework. So I did not want you to hit that and think, what in the world? 5,247.6. And again, I'm going to go ahead and approximate, bring this to the next whole number. So 5,248, I should have said, is the rounded value. So almost there. So this area in square feet is at 47,000, but in the square yards, again, square yards, there are 5,248 of those. All right, so let's get some space here. See what happens next. So again, what we're after is that we're covering this area to a depth of 2 inches. So that says that, kind of see if I can kind of give you a sense of this. It's like saying that this stuff is like the crust of a piece of pie, but I've got the pie piece itself, the pie stuff, down here below the surface. The pie stuff, and in this case that's dirt, is 2 inches deep. So everywhere I have a square yard, I need to multiply to get a depth of 2 inches. But this is inches, right? It's 2 inches out of 36 inches. I hope I'm thinking of this right. 2 inches out of 36 inches. In other words, that 2 inches as if it were cubic or yards, so that I can multiply in with the yards. It's basically 1 out of 18, 1/18 of a yard. 2 inches is 1/18 of a yard. So I've got my 5,248 yards squared times 1/18 of a yard. That's the depth, the multiplication in that direction, to get the depth. 2 inches to get the depth. So for every square yard I have out there in that field, I have to multiply to a depth of 1/18 of a yard to create volume. Okay, it's creating that depth, that volume. So I know this is sort of like, wow, this is what people really do. Apparently it is. So yard squared times yard is yards cubed. The 5,248 divided by the 18 is 291, approximately 6/10. The question was, how many cubic yards of topsoil are needed to make the depth of 2 inches? This much cubic yards of topsoil. About 292 cubic yards of topsoil would cover that field. All right, so that was hopefully to ease your way through a question like that if you see it again as you're working through your homework. If you have questions, let me know. And I would suggest maybe go back and, kind of stop this recording now and go back and actually re-listen to everything so that you really see sort of the entire flow of it, with it being a little more familiar. All right, there we go. Clear that. 10.1, I don't know, this section, it sort of looks to me like there's just a whole lot. You can see the slides, it goes on forever. There's a lot of topics all thrown into one big section. The 10.2 and 10.3 sections are much more focused, but this one just is kind of a big sprawl. And so I realized it seems like it is, the ideas are connected. They are related. They are related. It's not just a big hodgepodge, but it's, it's kind of a lot to put into one big chunk of learning and homework. Anyway, when an object moves along a straight line for a distance d and time t, its average linear speed v is defined as, well, we know this already. Velocity is equal to distance over time. This is not anything new to us. We know about rate times time is equal to distance. Linear speed, linear just means you're driving in a line, right? Down a highway. That's all it is. It's not anything that's unfamiliar at all. It's just that we've sort of changed up the rate and called it velocity. Well, that's the same thing. So we've already looked at this. We've talked about this in the course already. This is just exactly the same as saying that rate is equal to distance over time. So all of that you see down here. And it does come up though, compared especially to another idea. Let's do a linear speed. So we've got a car that travels 1,800 feet in 24 seconds. What is the average linear speed for the trip? So velocity is equal to the 1,800 feet. Now it is important to pay attention to the units here because this is not miles per hour. So the measurement here is going to come out in feet per second, 1,800 feet per second, or 24 seconds rather, by 24 seconds. So 1,800 divided by the 24, maybe you're looking at it, is 75 feet per second, 75 feet per second. It would be interesting to take that and know what that is in miles per hour. Could we do that? It's good practice. We might as well try it while we're here. So what that would require is conversions in both the distance, the feet measurement, and in the time. This is 75 feet per second. I'd like to get out of feet and into miles, because that's the highway measurement, right? Miles per hour. I'd like to get out of feet and into miles. Since feet is in the numerator, I'm going to throw it down here in the denominator. I'll put miles here because that's my destination unit. It's what I'm after. I know the equivalent here, 1 mile, is 5,280 feet. And if you didn't know it, you could look it up. But again, this is a good example of a time when it's very useful to use these unit multipliers because we don't have to figure out, am I dividing, am I multiplying, would I be doing something different for each of the units? Who knows? Let's find out. Seconds is over here in the denominator. I'd like to get out of seconds, so I'm going to arrange it so I put seconds in the numerator so I can cancel those units. I'm actually trying to get out of seconds and into hours, miles per hour. So can I come up with some relationship between 1 hour and some seconds? Well, yeah, if I think about it hard enough, 1 hour is 60 minutes. 60 minutes times 60 seconds per minute is 3,600 seconds. Say that again. Hour, 60 minutes. Each of those minutes is 60 seconds. So 60 times 60 tells us there's 3,600 seconds in an hour. So again, this is these are unit multipliers. They're fractions equal to 1. The advantage of going to this trouble is that I don't have to figure out the difference between multiplying by 3,600 and dividing by 5,280. I don't have to sit there and kind of snarl my way through that. I can be very sure that I know what I'm doing, that the calculation is right. Feet cancels with feet. Seconds cancels with seconds. I'm left with miles per hour. How cool is that, right? The units did what we wanted them to do. Miles per hour. And furthermore, I know exactly what to do with the numbers. I don't have to scramble my way around trying to kind of make sense of whether I'm multiplying or dividing. So I have 75 times the 3600 in the top, dividing by the 5280 in the bottom. And it turns out that this is about 51 miles per hour, a little bit more, about 51 miles per hour. So I took the time here, though the slide didn't ask for it, took the time to show you that conversion because it's good practice. I wanted you to see that and hopefully encourage you to practice that. Okay, that's linear speed as compared to this one. So the question is, watching that cat, watching that, whatever it is, piece of paper wadded into the fan. The question is something like this. The blades of the fan have a radius of 16.5 inches. And they turn one revolution, that is one full turn, every 0.125 seconds. They're really flying. Can we talk about linear speed? Yes, because if I think about what I'm asking myself is, how fast is the fan blade moving as it travels around that circle? But couldn't I, it's still linear speed, right? Because couldn't I take that red line and undo it and stretch it out and say, how fast is something traveling down that line? The circle is just a line that's bent, right? So how would I think about the length of that red line? What is the length of that red line? Well, it's the circumference of the circle. It's the circumference of the circle. So it's 2 pi r. So I end up being able to say that is something like, again, because we're in an application question, we're going to round this, take the approximation. So it's about 104 inches. That circumference is about 104 inches. If you run that calculation, 2 pi r, you should see that, about 104 inches. And this distance then, taking that again, that length of red is like straightening it out and saying, well, it's 104 inches long. It's 104 inches long, and it takes me 1.125 seconds to travel this far. That's the speed of the fan moving around. So it's taking me 1.125 seconds to travel that 104 inches. So clearly, again, though it's about a fan, this is something that we can calculate as linear speed. The velocity would have to be the distance, the 104 inches, divided by the time, 0.125 seconds, which as a calculation amounts to 832 inches per second. Pretty fast. Seems really fast to me. 832 inches per second. I almost said, do you have questions? But then you're not here to answer. So if you have questions, let me know. Okay, please do. I suspect that that's an unrealistic speed, but that's the way the numbers came to us, so we'll let it be. Okay. Angular speed. So think about the one that we just looked at. What we were asking ourselves was, something like if I had a fan and I took a, sort of a marker or something and messed up one of the blades. My kids used to do this, draw little things on the fan blades and watch it spin around. So if I marked the very tip of one of the fan blades and I thought hard enough about it, I could figure out how fast that little blue tip is moving around the circle, right? That's one way to think about the speed, but another would simply be to say, how fast is the angle around the middle changing? As the fan blade moves around, what is the speed of the change in the angle? That's angular speed. But it should make sense to you that if we say that A is the angle in radians, that the angle in radians compared to time should give us the angular speed. How fast is the angle changing? So we take the angle compared to time, and we could answer that question. And so let's do some of that. Average angular speed. Here's an example. Suppose, let's see, yeah, that's moving. So suppose you have to calculate the angular speed of a flywheel. If a 24-inch diameter flywheel rotates through an angle of 140 degrees in 1.1 seconds, what is the average angular speed, W, of the flywheel? First, we have to convert the degrees to radians. All right, so let's do that. Let's get the degrees converted to radians and we'll work on the rest of it. So the 140 degrees, I'm multiplying by pi over 180. And I know to put the 180 in the bottom because I want to force the degrees to cancel. I end up here with basically 14 pi over 18, which is going to be what? 7 pi over 9. That's the exact value of the angle. And I want to find out. So the span, the change in the angle, in other words, is from, say, 0 radians to 7 pi over 9 radians, or 140 degrees, in a certain amount of seconds, in 1.1 seconds. This is the 140 degrees in degrees. It's the movement is starting at some initial stationary spot possibly, and thinking about how long does it take to get that 140 degrees covered. It takes 1.1 seconds. Well, then what is that speed? Because distance divided by time should give me a speed. So my angular speed would have to be the 7 pi over 9, which is the A, the angle, divided by the 1.1 seconds. So go ahead and try that, see what you see happening, and I will do the same here. And you should be done. Calculation is easy. Don't be thinking it's going to be nasty. It's just put it into the calculator. So 2.22, more or less, what would that be? What is that speed? Well, remember, my angle is in radians. So this is about 2 radians per second, given that my angle is in radians. It's about 2 or 2.2, a little more than 2 radians per second. Angular speed. So that angle is changing at a rate of about 2 radians per second. Okay. Okay. Here's another fun one. Calculate angular speed of a Ferris wheel. So a certain Ferris wheel takes 23 seconds for each revolution. Again, each revolution means all the way around. 23 seconds to make that distance. What is its average angular speed? Convert, degrees to radians first. Well, what are my degrees here? If I start, maybe you're in that car that's sitting up there at the top and you can see everything and it's the scariest thing. And then, you travel backwards, you sit there and go backwards, and then you come and you go forward and you get back to where you started from. That's a 360-degree span, right? Of course. You've traveled 360 degrees when you go all the way around. So what is that in radians? Maybe you already know, but if you're not sure, you could certainly take a look using your unit multiplier. That is 2 pi. 2 pi radians. And again, be careful, because remember that this formula only works in terms of radians. It's in terms of radians. So the angular speed here is asking us if it takes 23 seconds to travel 2 pi radians, how fast is that per second, in 1 second? How fast is that in 1 second? 2 pi divided by the 23. So that says my angular speed is about, again, depending on how you're asked to round something, about 0.27 radians per second. Not quite 3/10 of a radian per second. Those are, again, I know those that speed in terms of those units, radians. It's difficult to sort of get a sense of, is that fast or is that slow, because the units are unfamiliar to us. All that says is, be careful and double check everything as you're working these, because the numbers may not intuitively, you can't really judge whether they're reasonable or not. I realize that. So again, what we said was the 360 is 2 pi radians. All the way around the circle is 2 pi radians. The 2 pi radians divided by the time, 23 seconds, would give us the angular speed, about 20.27 radians per second. So as the Ferris wheel is turning, this angle in the middle is changing at a rate of about 0.27 radians per second. Okay, angular speed. Let's do some more. So we jump now into sort of what looks like an entirely different topic in the same section, 10.1. I don't know why it's doesn't get its own section. It seems like it would. But we're ready to now talk some about right triangles. Right triangles. Trig. We're doing trig. Yeah. So you guys have to do some trig. Trigonometry means triangle measure. Triangle measure. We're going to start by studying only right triangles. And you'll know that a right triangle is one that contains a right angle, 90-degree angle. All of these are right triangles with the right angle marked. Okay, so right triangle contains a right angle. So it sometimes helps as you're working on these sorts of problems, if you see a sketch of a question, a triangle in a question, you may want to redraw it to get it sort of oriented in a way that makes more sense to you. This one here is in what we call standard position. I think also this is a convenient orientation. But a lot of times something like this or this, I have to stop and redraw it and turn it around thoughtfully. And it's not even always easy to get it right and do that. Be careful. So you may, though, want to reorient the triangles at times. Okay. And parts of a right triangle. Right triangle has special names for different segments of it. The two sides that are kind of adjacent to that right angle, we call the legs. And the longest side here, we call the hypotenuse. Hypotenuse. Longest side. It's always the hypotenuse, so always the side that's opposite the right angle. I know that you'll remember some work with Pythagorean theorem, which is for finding the lengths of sides. This is for finding the length of sides. If we have any two of the sides, we can find the third one. C squared is equal to A squared plus B squared. So let's practice doing that. Here you go. So find C. So I'm going to have do this one with you. C is always the name for the hypotenuse. I'll do this one with you, and then there's a slide coming where I'll ask you to complete that for an activity to turn in. So C squared is equal to A squared plus B squared. It does not matter which leg is called A and which is called B. Makes no difference at all. That doesn't concern anybody. So we've got this 36 squared plus the 15 squared amounts to 1521. So again, you should be tracking that calculation with me, doing that with me. The question then is, how do I get just plain old C? Because right here I have C squared. So I hope you'll remember that our, sorry, the wrong thing. Let me redo that. Hold on. I hope you'll remember that the process here to come out of C squared and just have C by itself is what we call taking the square root. We're taking the square root of both sides. Take the square root of both sides. That's the language we use. Take the square root of both sides. In the calculator, you would find probably for the TI-30 at least, you would find your second and then caret key. Probably you know where this is already, but just in case. Or second in an X squared key, right? Let me show it to you. So the second key up here gives us the functions that are above the keys as they're stated. So down that left side column on the TI-30, and yours will be similar. It's a different calculator. If you want the square root function, you hit second and X squared, and it will then let you access that square root sign. So square root of 1521 is, oh, that's perfect square. That's handy. Exactly 39. So C is 39. Also, again, as you work on these, you always want to look and see, does that make sense? The hypotenuse is always going to be the longest side of the triangle, so that's reasonable. Also, it's a number that's kind of in the right neighborhood. You know, if it said 390, I would say, well, that doesn't make sense because it can't be that different from those two side lengths. It's a number that's similar in magnitude to those lengths, and therefore it is a reasonable result. So your job here, oops, yeah, 10, 1, 13 is to find Not the hypotenuse, but the missing leg. Missing leg. Find this length. And that's not the hypotenuse. The hypotenuse is the longest side. It's the side that's opposite the right angle. So here that C value is 19. So your job is going to be to work backwards out of the given information to find the missing leg. And again, if it helps some, you could redraw this and kind of get yourself looking at it a little differently. The side opposite the right angle is 19, and one of the legs was 9. So you're looking for this distance right there. So I will leave you to make your way through that, answer that question, show the work, and make sure that you have indicated on your page that this is in-class activity, day 12, number 2. Make sure you mark that and label it. I'm not going to spend time hunting through a page of, other material to find where you might have solved this. So you have to indicate and mark that for me to make sure I see where you are. Okay. All right. So I'll leave you to think that through. And if you have difficulty, question, let me know. And let's talk about cathedral ceiling. We seem to see this one a lot, like a perennial word problem. Cathedral ceiling creates the interior wall shown in figure 1. Find the length Y of a beam that is needed to go along the top of the wall. So if you were really clever with your trapezoid stuff, you could find this by way of recognizing that you're looking at a trapezoid. You definitely are looking at a trapezoid. The two bases in the trapezoid are the 8 feet and the 12 feet. And you could come up with that distance Y, some enabling with your trapezoid ideas. But if you want to also think of that in maybe what's a little more intuitive way, you would be thinking possibly about this as a right triangle question. That's why it's in the slides where it is. It is a right triangle up there. And furthermore, I know something about it. I know that this leg is 22 feet because it's going to be the same as this one, its distance. And I know that if I've got an 8-foot wall here, 12 feet here, that this has to be 4 feet. So that says I could easily find the length of Y using my Pythagorean theorem. This time, the C squared is just called Y. It doesn't matter what it's called. Call it Henry if you want to. And that distance, that was Y squared, will be equal to the 4 squared plus the 22 squared. And again, I think that you'll see something like this in the homework. So this is hopefully going to set you up to have good understanding of that when you see it in the homework. So 16 plus 22 squared becomes, gosh, that makes me crazy, sorry, 500. Y squared is 500. Again, though, Y squared is not what I want. How do I get Y by itself? I take a square root of both sides. Square root of Y squared is Y. Square root of 500 is approximately 22.4 feet. You should be looking at that, seeing that in your calculators, 22.4 feet. As well, and again, this is an approximation. Just for the practice, let's talk about that 4/10 of a foot. Remember that this is not 22 feet 4 inches. I promise it's not. Because that 4 is not inches, it's tenths. It's tenths. It's tenths of a foot. It's not inches. And so, how do I get out of that into inches? I take that 4/10 and multiply it by 12. So it turns out this is 12 inches, right? So now I'm looking at 4/10 of 12 inches is 4.8 inches. So this amounts to about 22 feet, 5 inches. So if you were needing to give this in terms of feet and inches, you could say approximately that it was 22 feet, 5 inches. All right, that's that. Now we get the fun stuff. Special right triangles, 30, 60, 90 degree triangles. 30, 60, 90 right triangle, whoops, is of special, oh gosh. Won't let me pick up the pen. There we go. Is of special interest to us for a variety of reasons, as you'll see as we work through some more of the trig. So we learned something about these. This shows up quite a lot. And so what this says is that if I know that I have 30-degree angle here, 60-degree angle here, I can say something about the relationship of the side lengths. If I don't know, the side opposite the 30 degrees is going to be the shortest one, right? Because 30 is the smallest angle. So if I don't know the length of that smallest length there, smallest side, I could say it's X, meaning I don't know what it is. But it turns out, if that's true, and I have a 30-degree angle, 60-degree angle here, I don't know what this length is across from the 30-degree angle, I could know something about the hypotenuse though, and I could know that it is a length of 2 times that X, 2 times X. And furthermore, that this thing will be, that longer leg will be X times the square root of 3. That may not even make any sense to you at all. We could look at it with some numbers. So for example, if X say is 5, maybe it's 5 inches. I know because it just always happens this way with the 30, 60, 90 relationship there. I could know that my hypotenuse, if this is 5 inches, my hypotenuse has to be 10 inches. 2 times the 5. And I could know that down here, this third side, that leg that's horizontal, is 5 square root of 3 inches. Awkward, but true. 5 square root of 3 inches. Okay, so this is an important set of relationships that we use a lot in various trig kind of thinking about some things. So here are a couple more examples. The first one says that if B, so if A is the 60-degree angle, and that makes this a B. So if B, if this length over here is 8 feet, if that length is 8 feet, then the distance here, hypotenuse, is 2 times B. This would be 16 feet. And this distance down here would be 8 times square root of 3. Those relationships are always true. They're always true in a 30, 60, 90 triangle. Okay, so let's do something with that. So we are here. Find missing lengths. So if A is the 60-degree angle, right there, the side, and the way these conventions, the naming conventions go is that you use capital letters for the angles, and then you use the corresponding lowercase letter for the side that is opposite that angle. So if this is angle A, this has to be side A. If this is angle B, this has to be side B, and so on. So that's standard. You'll see that, repeated, and you'll be using that idea. So if A is 60 degrees and this, we are told, is 32 yards, opposite there, then B over here has to be, well, let's do C first. This is easier. The hypotenuse. The hypotenuse is, again, twice the length of the shortest side. But I don't know what the shortest side is yet, right? Because I got the A value, that's the longer of the two legs. The side opposite the 30 degrees will be the shortest side, and that is my B. Well, I can find my B if I know A. I can find my B in this case by dividing that 32 by square root of 3. So this is a helpful little idea here. You might want to make sure you know how to find that in the notes there. That if you're given the longer leg, you can find the shorter leg. Instead of, multiplying by square root of 3, you'd be dividing by the square root of 3. So this B distance is 32 divided by square root of 3. That's the shortest leg. So C is twice that, 64 over square root of 3 in this case. Okay. Again, if you need help with that, questions, let me know. Send me something. Email if you need to. So you see a little summary here of what we've said so far. If you're given the length of the shortest leg, one that is opposite the 30-degree angle is the shorter leg. If you're given, when given, the length of the shorter leg, to get the length of the hypotenuse, you're going to multiply that by 2. To get the length of the longer leg, you're going to multiply that by square root of 3. If you're given the length of the hypotenuse, if you divide that by 2, you get the length of the shorter leg. And then you can take that shorter leg, multiply that by square root of 3 to get the longer leg. In other words, in a 30, 60, 90, you only have to be given one of the side lengths, and you can find the other two as a result of these relationships. When given the length of the longer leg, divide it by square root of 3 to get the length of the shorter leg, and then take that shorter leg multiplied by 2 to get the hypotenuse. So that slide may be some help to you. You can kind of keep your eyes on that, refer to that, come back to it if it would be useful to you. All right, so find a missing length. Here's a word problem that's kind of interesting, challenging. The dashed line here, it says, shows where a cut has to be made in a rectangular piece of sheet metal. Find the length of X. This distance, we need to find this. So let's think about what we do know. We know that this much is 18, and this is a rectangle, so this total has to be 18. That's something. We know that this length is 28. If this much is 12, then we know this much has to be 16. That's something. And so, again, really what we're interested in, what we need here to answer the question, find that X, we really need this distance, right? We need that length, because we could take that off the 18 and we get the X. So we've got a 30, 60, 90 triangle here. I'm going to sort of pull it out separate. We've got a 30, 60, 90 where we know that the longer leg is 16 inches. We know that the 30-degree angle is up here. And we know that the 60 is down here. So what we really are missing, what we need to get hold of up front, is to get the length of that shorter side right here, right? If we could get that, that's what this is. And we'd know how to find that X value. So we've got the length of the longer given. We need to find that smaller segment. In general, let me repeat these relationships so we'll have all that in front of us. So the shortest side is always across from the 30-degree angle. That's X. Hypotenuse is 2X. This is X square root of 3. So what that says to us, again, is this is what I'm looking for right there. If I can find that, the 16 inches is that X square root of 3. So again, you can see this referred to in the slide above that we just moved away from. If I have that longest side length and I divide by square root of 3, I'll be able to name the shorter side length. That shorter side length is 16 divided by a square root of 3. That value, you know, again, this is an approximation, but that value is about, if you look at it in your calculator, is about 9.2. And as I was working on this, I practiced this and was looking to see how precise this needed to be in order for it to, you know, actually work. And so it turns out in this case, 9.24 is the better approximation for this distance. 9.24 is this distance, which says then that the missing X value there that I'm actually hunting is 18 minus that 9.24, which makes that what, 8.78? Let's check. So, hold on. Let's do that again. So 18 minus the 9.24. 8.76. That makes more sense. Okay. The reason I'm saying take that out to 2 decimal places, these are in inches, is that what I did was I did a little check of all of this. How would I check this? Because I wanted to, again, just to see how precise it needed to be. So what I did was I did a little Pythagorean theorem work. And when I used, to check it, when I used, this was the 9.24. When I used 9.2, I was looking to see if I got the right numbers, in other words, to make it consistent with the relationships that we were given. And when I got, if this is the longest side, the shorter side is 9.2, 2 times that for this hypotenuse is 18.4. And if you check that in Pythagorean theorem, it doesn't quite, it's off a little bit. The 18.4 squared doesn't quite match those two squared and added together. But I found that if I brought that out by one more decimal degree or decimal place, I brought that out by one more decimal place, then I got something that was consistent inside Pythagorean theorem. So that's what I was doing, is checking to see how precise it's needed to be. So this is about 8.76 inches, about 8 3/4 inches. You could, you know, measure it reasonably that way. All right, so let me know if you have questions. Again, that relationship is always the same. The shortest side across from the 30-degree angle would be an X. This is 2X, the hypotenuse. That third side would be X square root of 3. So what I did was take that given 16 inches, use that to name my X. Shortest side is that. I used 2 places to get that to be precise enough, 9.24, and to get this value, I subtracted the 9.24 from the 18. Ta-da. Okay, lots going on today. Here's another that you maybe would like a little better. Special right triangle, 45, 45. And this one, you know, kind of predictably is a little tamer to think about. The relationship among the side lengths, again, will always fall in this ratio. 45 degrees in each of those angles creates a side length. The legs are the same size of 1, and the hypotenuse will always be square root of 2. Again, that doesn't say the length is going to be 1. It says, suppose this is, say, 20 inches, and this side is 20 inches. They'll be the same. Then this side will be 20 square root of 2 inches. That's the idea, okay? It's that relationship among the side lengths, ratio of those. Here's another example if you want to see it again. If this is 5 inches, this would be 5 inches. This side would be 5 square root of 2 inches. So this one is a little tamer to think about. Also, what's interesting about 45, 45, 90 triangle is that you can build these out proportionately without changing the angles. Of course, this down here, the little one there is 45, so the one up there in the tighter corner, get stylus where I can. It's hard to write in these small spaces with a blunt stylus. I apologize if this becomes kind of a mess, but that's 45 degrees also. It turns out that if you extend the leg, make the leg longer, and make the leg longer by the same length. Of course, the angle is, think about it, you know, you're just looking at corresponding angles. The angle measurements don't change. This is still 45. This is still 45. So all three of these are have the same angle relationships. They're all 45, 45, 90 right triangles. If we increase the length of one side, the other sides increase in proportion while the angles will stay the same. And the interesting thing then about that is it turns out that there's sort of a family of these, which really we get down here. Actually, this is different, different scenario. But anyway, so let's go ahead and take a look at yet another version of these right triangles. And that is a 3, 4, 5 triangle. What we just said was that if we had a 45, 45, 90, just to reiterate, so I'm not confusing anybody. If I have a 45, 45, 90, that previous slide was trying to make the point that if I extend, pardon me, I'm trying to get this to cooperate and get this stuff that I don't ask for. If I extend this leg by a certain amount, and I extend this leg by a certain amount, and the lengths are this is the same amount of increase, that the angle measures don't change. That was the point on that previous slide. What this one is about, this slide is saying that if I have a triangle that has this relationship, 3, 4, 5 distances, and I'll show you what I mean by that. So it's kind of reasonable. That says, if I know that my shortest side is 3 and the other leg is 4, I will know that this is a length of 5. How would you know that? Well, think about your Pythagorean theorem. Because you'll see, that it actually works out that way. 4 squared is 16, 3 squared is 9, 5 squared is 25. So anytime I have a side length of 3 and a side length of 4, I automatically know that that side's going to be 5. But I also know something even more helpful, and that is, what if I said, well, I have a right triangle. Oops, it's not very much of a right triangle. I have a right triangle where I have a length of 6, length of 8. It's not to scale, so again, don't worry about that part. But suppose I have a length of 6, a length of 8. I automatically know that here I'll have a length of 10. How did I know? Because 6 is 3 times 2. 8 is 4 times 2, and therefore my hypotenuse in the new triangle will be 5 times 2, 10. So we end up with this sort of family, so to speak, of 3, 4, 5 right triangles that we can get by multiplying the 3, 4, 5 by some number. And I would know that I still have the same relationships all the way around the triangle. This could be a 15. This could be a 20. This would be a 25, everywhere multiplied by 5. And that way, if I know 2 of the side lengths, I can always get the third. If I know they're 3 and 4, I could get the 5. But if I know that they have that 3 and 4 relationship, 15 divided by the 5 would give me the 3. 20 divided by the 5 would give me a 4. If I know that they have that proportionate relationship, 3, 4, 5, all the way or on the legs, then I also know something about the what the hypotenuse will be. It'll also be whatever that number was multiplied by that original 5. So the 3, 4, 5 builds out into, all kinds of other lengths that have that same 3, 4, 5 relationship. And the angles will be the same. That's the critical idea there, is that the same angles then will show up in any 3, 4, 5 multiple. The angles will be the same no matter what those side lengths are. If they're in that 3, 4, 5 relationship, the angles are the same. So here's one that's an example. This is proportional to 3, 4, 5. That is, I know that that's true because when I look at the 6 and the 10, I can see that relationship. 6 divided by 2 would give me a 3. 10 divided by 2 would give me a 5. So I can tell that this is a 3, 4, 5 triangle. This side in the 3, 4, 5 scheme would be a 4, but it's multiplied by 2 because that's where these came from. 6 and 10 came from those original values multiplied by 2, and so this side has to be 8 feet. So it's kind of cool. It's useful, the 3, 4, 5 idea, portions that way. That is the end of 10.1. Hope you're not exhausted. And we're going to go ahead then and take a look at 10.2 and 10.3. All right, this is 10.2, section 10.2, trig ratios, We do not necessarily assume that you have had any acquaintance with these, but many of you will remember that you've done a little trig along the way in high school, possibly, I'll say possibly. Again, if you did, then you'll remember some of this, and if not, it's okay, because we're going to assume nothing and start from scratch here. So we're going to find the values of trig ratios. We're going to find the angle when given the value and solve problems. That doesn't mean probably much to you right now. That's okay. And so the first thing we want to recognize is that in a right triangle, which you see an example of here, we've talked about the fact that we call this distance, the longest distance, the one that is across from the right angle, that we call that a hypotenuse. We've referred to that previous to this time, but we have not necessarily used these other pieces of language. So I want to point out here that if I'm thinking about angle A, I call this side that is, it forms one side of the angle itself. That side we call adjacent to angle A, while this is clearly opposite. So we want to be bearing down on these ideas of the side adjacent and the side opposite to a certain angle. So for angle B, the side opposite is there, this one. For angle B, A is the side adjacent. So when we start orienting to using that language, we'll need that. So we define a particular pair of, or a particular set of relationships between side lengths in different ways. We call the first one sine, abbreviated this way. It looks like sin, but it's pronounced sine. So the sine ratio is defined to be the side opposite an angle, the length of that side, compared to the length of the hypotenuse. The sine of A is the length of the opposite side divided by or compared to the length of the hypotenuse. It generates a certain number, It's a number without units. It's not like a certain measurement. It's just a number itself. It's a relationship between two measurements. It's a ratio. The sine of B, for example, here, again, would be the side opposite B compared to the hypotenuse. So sine is always defined that way, opposite over hypotenuse. So we would say here, for example, in this triangle, the sine of, oops, that again. What's that about? The sine of that 36-degree angle is the length of the opposite side, the 52.9, over the length of the hypotenuse, 90, which amounts to about 0.588. It turns out what's interesting and important here is that this number is not only just true for this particular triangle. Any 36-degree angle will always see this relationship, the comparison of the side opposite to that 36-degree angle compared to the hypotenuse of that triangle, believe it or not, will always be that 0.588. The sine of 36 is that number, period. And again, it's a number, it doesn't have any units, it's the comparison of the two side lengths. We have, let's see, whoops, this one. We have, sorry, let me come back to where we were. So in terms of sine, we want to go back and look again at these special right triangles that we just discussed, the 45, 45, 90, the 30, 60, 90, and the 3, 4, 5, which is again referring to those side lengths, not the angles. And we could use what we know about those to actually define all of those values the sine of all those angles. Sine of 45 degrees means take a look at your 45-degree angle, look at the side opposite. If that length is 1, the side hypotenuse side would be square root of 2. Sine of 45 is 1 over square root of 2. Sine of 30. Sine of 30, again, is opposite over hypotenuse. Sine of 30 is 1/2, and that's true for all 30-degree angles, not just this particular scenario that we're looking at. Sine of 60 is opposite over hypotenuse. Sine of 60 is square root of 3 over 2. Regardless of the triangle, if you have a 60-degree angle, that sine is square root of 3 over 2. Sine of 37 degrees, we could pull that out of this one. Regarding that 37-degree angle, the opposite side has a length of 3. The hypotenuse has a length of 5. Sine of 37 is 3 over 5. Sine of 53, you can see where that's headed, is going to be, so I'll mark it so it looks better. So sine of 53, we're thinking about this angle. The opposite is the 4, hypotenuse is 5/4. Okay, so that is sine. What that has, the use of that, we're not trying to necessarily describe right now. We want to just be practiced up with how that comes about, what the calculation looks like. And you should realize that there are actually 3 of these trig ratios that we're going to be bearing down on in this course. Sine is the first one. The next one is cosine, abbreviated COS. Cosine says, if I am referring to angle A, cosine says I should compare the length of the adjacent side, not the opposite, but the adjacent side to the hypotenuse. So for this triangle, cosine of angle A is that B over C. If I wanted to refer to angle B, the cosine of B, I would say it is that side adjacent length, A, compared to the length of the hypotenuse. Cosine, again, adjacent over hypotenuse, that's the second of the 3 trig ratios that we need to practice up. There are actually 6 of those, but we're only learning 3. The other 3 are sort of derived from these, so 3 is really the whole story in that way. Find a triangle to practice. There we go. So let's practice cosine. So cosine of 36. 36-degree angle, again, would give me a relationship of comparing that 65, which is the adjacent side. It forms one of the arms of that angle. 65 compared to the hypotenuse, 80.2. So we say the cosine of 36 degrees is about 0.81. And again, that's true, period. Doesn't matter where that 36 degrees is located. 36-degree angle for any triangle will always have a cosine of about 0.81. The third ratio is called tangent. And in this case, referring, for example, to angle A, tangent is defined to be the opposite length over the adjacent length. Opposite over adjacent, in that example, A over B, or the tangent of B over here, again, is opposite. So it'd be this B length over adjacent, A, B over A. And that's basically it. Those are the three in the three relationships. Let's practice the tangent, and then we'll remind ourselves of how we can remember all this. So the tangent of 33, again, says I need to compare the opposite side, 13.7, to the, oops, I lied, to the adjacent side, 21.1. Opposite over adjacent. Adjacent is lying where it helps to form the actual angle that you're looking at. So it's the one arm that's helping to form that 33-degree angle. It's, is never the adjacent is never the hypotenuse. I should maybe say it that way. So the hypotenuse is hypotenuse. It's never going to be called anything else. Adjacent then has to be, if I'm thinking about this 33-degree angle, this can't be it. It has to be this one. And again, that ratio, that 0.65, is the tangent of 33 universally, regardless of where that 33-degree angle happens to live. And you may remember then this little guy, SOHCAHTOA. If you had some trig in high school, you definitely had this, and you'll definitely remember. It's a little mnemonic, excuse me, device to remember something, just like PEMDAS helps us remember order of operations. So this helps us remember the trig definitions. The S is for sine. This is opposite over hypotenuse. The C is cosine. This is adjacent over hypotenuse. This is tangent, opposite over adjacent. So if you can remember SOHCAHTOA, you'll have basically all of those definitions memorized. Also be aware, though, that these will be available and defined for you on a formulas sheet for the exam. By then, though, you may not need them. But if you do, you'll have them. So it turns out that we use the calculator rather than, because we don't always have a diagram that's giving us lengths of sides and so on. We may not have that information. But the calculator can give us the trig functions for any angle. Sorry about that. To make sure that your calculator is ready to do that properly, you want to go in and find your mode button on the TI-30 XS multi-view. Is going to look like that in the top row. And if you hit that mode button, you should be doing that now. If you hit that mode button, what you'll see is that first row opens up. Oh, it's sort of three options that look like this. That stands for degrees and radians and something else there. So you want to make sure that your calculator is highlighted. Sorry, I've been doing this for a couple of hours. My voice is going. Make sure that your calculator is highlighted to choose degrees, so that when you look for these values, you're actually getting those calculated in degrees and not in something else. Okay. Having said that, then let's talk about how we would actually go about doing that. The next slide gives some information about calculating with degrees and minutes, and I actually think that's probably not something you're going to have to do a lot of. So I'm going to actually just give you some practice here, and give you some angles to think about. So I would like you to look for in your calculators sine of 75 degrees. How about cosine of 37 degrees? Trying to make something that we didn't already do. And let's find tangent of, let's say, 14 degrees. So in your calculators, please go ahead and look for that. The way that you do that, if you're not sure, for example, sine 75, is that you find your sine button. It'll be labeled SIN, sine. Hit that, and then just enter the 75. And you might get some kind of, if you get something that looks strange, that is, if it doesn't give you a decimal approximation, it's giving you a sort of an exact value version, which is not in most cases what we want. And so you can hit your toggle button and kind of make that go away. So when we check that, then sine of 75, again, if you get something that gives you the exact value and it looks like it's got square root signs and so on in it, you can hit that toggle button that's down there by your enter key, and that toggles back and forth between exact value and approximation. So it will give you the decimal approximation for those numbers. So you should be seeing 9659. Many times we use 4 decimal places to refer to these trig function values. Cosine of 37, then go ahead and find that in tangent of 14 if you haven't yet. Pause the recording and check those out. And then we'll look at that together. And so we should say approximately. So the cosine of 37 you should be seeing as approximately 7986. The tangent of 14 degrees is approximately 2493. Okay. The last thing I want us to think about is, again, a very helpful situation. And that is what we've done so far is we've looked at the given degrees, given the angle, and found the trig ratio. But shouldn't it make some sense that if I knew the trig ratio, I should be able to go back and find the angle? Is there a way to do that? So what I would have you do is take your calculator and hit your second key, second, sine. And when you do, you'll see it opens up this thing that looks like that. And we call that sine inverse, sine inverse. And what it says is, if you tell me, calculator saying to you, if you tell me that sine number, I would be glad to tell you what angle made it happen. So we can go backwards here. If we know the given ratio, we can find the angle. So again here, cosine inverse of 0.7986. You should be doing this in your calculators. Cosine inverse of 0.7986. You should be seeing, calculator says it's 37 degrees. Now you see, of course, a little bit of stringy decimal there. These are not precisely showing up as 75 and 37 because the trig ratio values themselves, we've rounded. These are rounded. However, you can see that we're getting, what we expected. These are virtually the same measurement. If I go in and use my inverse tangent, so I hit second tangent, And I put in the given ratio, 2493. And, oh, I got a syntax error. Didn't put it in. 2493. Trying again. And again, it's very, very close to that 14 degrees. That was the angle that we started with on the other end. So tangent inverse, cosine inverse, sine inverse, we can get those out of the calculator as well. If we know the ratio, we can find the angle that made it happen. And that is really the solving right triangles. This is where it gets to be kind of fun. This is where we've got the skills in place to make a little bit of a game of this. It's like solving a puzzle a bit. And that is solving a triangle means, it sounds like it's sort of a vague thing. What's that mean? Solve a triangle. But it has a real specific meaning. It means find all the side lengths and all the angles. Find all the side lengths and all the angles. And so, we've got tools in place to do quite a lot of that already. Because, for example, here, these are right triangles. So we know if this is 90 and this is given as 50, we know that the total has to be 180 degrees. So we know that this has to be a 40-degree angle. 50 and 90, 140, another 40 to make a 180. So we know that. We know that much. That's easy enough. We could also find this length A and this length B. How would you do it? Think about that a little bit. How would you do it? So we're not looking at a 30, 60, 90. We don't have that relationship here. So that doesn't apply. It certainly isn't the 45, 45, 90. It's not the 3, 4, 5 either. What could we do? Could we start possibly by saying, well, this is a 50-degree angle. And I know something about the sine of a 50-degree angle, that it would have to be opposite over hypotenuse. And I know what the hypotenuse is. That's a known. That's 21. Since I have, of course, my calculator, which would give me sine of 50 if I asked it quite happily, couldn't I actually get to the opposite side length if I said, well, calculator, because I'm going to multiply both sides by 21 to clear that denominator. Calculator, please tell me what is 21 times the sine of 50 degrees. Because when the calculator does that for us, 21 sine of 50, you go ahead and try it. Doesn't that have to give us that side that is opposite? It's about, and again, I'm rounding a bit, it's about 16 centimeters. You'll see that in your calculators. How cool is that, right? Couldn't I also then find that length of A in some similar fashion? I really have more information now than I need, but I could consider in relation to that 40-degree angle, for example, I could use sine again. I could say, well, sine of 40 degrees has to be opposite over hypotenuse. Hypotenuse in this case is still 21. If I want to clear that denominator, I can multiply through by 21 on both sides. 21 sine of 40 degrees has to give me that opposite side length. So go ahead and do that. 21 sine of 40. And again, you'd have to round this somewhat. It's not, feasible to get this in. It's not going to come out evenly. It's not your problem that it doesn't. It's just what the relationships are. But it will round to about 13.5 centimeters. 13.5 centimeters, that opposite side. So we solved it. We solved the triangle. We got all the angles and all the side lengths. And you could also and should double check. How could you check to make sure that this is correct? Well, we know, of course, the angles all add up to 180. That part seems to be all right. But could we check the side lengths by running those through Pythagorean theorem, knowing that we have made a little bit of rounding, so we don't expect this to be precisely correct, but roughly 21 squared ought to equal this 13.5 squared plus 16 squared. It ought to come out that these two sides are about the same, very close to the same. So go ahead and take a look at that. 21 squared, 441. And again, we're not expecting precision, but 13.5 squared plus 16 squared. So what you see is in this example, 438.25, as I said, remember that we did some rounding on those side lengths. And so we don't expect that this was going to come out precisely to 441, but 438 is pretty close. So we have reasonable approximations of those lengths. And again, depending on the circumstances and directions, you might have to round a little more precisely. We'll see. Just do whatever the problem asks you for. Solve the triangle. So here's another one. And now what? So here we're not given any of the angle measures at all. We're given two side lengths, and that's it. Of course, the right angle. And then we have two side lengths, and that's it. Now what? Okay, so, well, what could we say? In reference to angle A, what could I know? In reference to angle A, what is the known? I know an opposite, and I know an adjacent. So, what could I say? Couldn't I say that the tangent of A has to be opposite over adjacent? I'm not really hunting the tangent of A. Those numbers are there. I was given those. There's nothing to discover there. But couldn't I find my angle if I thought about the inverse? The inverse of that given set of information, that given trig ratio. In other words, this is some decimal. I haven't, laid it out, but the calculator doesn't care. If you really want to see it, you could go ahead and look at it. 11.3 divided by 16.5. The tangent of this angle A, the tangent of that is about 6.848, right? You see that in your calculators if you're looking. The tangent of that angle is about 6.848. Can't I use this to work backwards to find what angle created that tangent? So I go in, I hit my second tangent, and I get my inverse tangent. And I'm actually going to go back and just use the precise values. 11.3 divided by 16.5. I'll get a more exact answer that way. And the calculator will tell me Not a problem. That angle that made that happen was about 34.4 degrees. You should be seeing that in your calculators. Make sure you see where that came from, 34.4 degrees. From there, could I solve the rest of the triangle? I'm sure you can. You know how to find the other angle for sure. You also could find several correct ways to see what that hypotenuse length is. More than one right way to make that happen. Just find that hypotenuse. So I'm going to also give you this one to finish out as an in-class activity to finish it. So you'll find this angle here and you'll find that hypotenuse in class. Oops. Activity. And make sure that you mark the page or the problem. Make sure that you mark that very, very clearly for me. In class activity, day 12, number 3, I think we're on. Make sure you mark that very clearly on your document and show the work, and solve the triangle. Okay? Clear that. There's one more for practice here. I think because of time, we'll perhaps try to save this as a review to pick up and look at the first part of class when we come back to start 10.4. So I'll try to remember to come back and pick up 10.3.3 just to, as a review, to kind of recap before we move on into the new 10.4 material. So I'll leave 10.3.3. You guys remind me if I forget that we want to come back and take a look at that. This is a very interesting question, and we'll wrap up with this. Trig is very, very practical, and it has been used for many centuries to make all kinds of measurements in surveying. George Washington learned trig and was using exactly the same information that you guys are currently learning. George Washington was a surveyor as a young man before he became president, and he had to do stuff like this. Literally, I'm sure. I'm not kidding. So suppose that you needed to measure the distance between points A and B that are on opposite sides of a river. And you have a tape measure and a protractor. So you have some kind of way to measure a distance this way. And you have some way to measure an angle. But no, you don't have any way to get across the river and actually stretch the tape measure across the river. That's not going to happen. So suppose you took your tape measure and said, well, I don't know what else I can do, but I can measure out a distance like this. And maybe you measure that and you say, okay, I just measured out or walked off maybe, we'll say 17 yards. You could even do it roughly, you know, even without a tape measure. If you took a step that your normal stride is about a yard, you could just take 17 paces even and get a pretty good approximation of that distance. And then maybe you also have, as we said, a protractor, and you could sort of sight, you might have to sight it, that angle, and maybe you could get that angle figured out right there, that angle, and maybe that angle is a 43-degree angle. Given just the 43-degree angle and the 17 yards, couldn't you find out what that length is using some trig ratio? Think about what's known and what's unknown. Your known would be and adjacent and the angle itself. Your unknown is an opposite. What could you do to find that distance from B to A? So I'm giving you this as a fourth problem, and that will also then be sure you indicate for me. But I've given you enough information that I think you can walk yourselves through what needs to happen there, considering that you're thinking about an adjacent in relation to that opposite. Which trig ratio uses those two distances, an opposite and an adjacent? Think about which trig ratio that is. You've got the angle. So in class activity, day 12, this will be number 4. So you'll get that worked up and get that turned in for me. Make sure it's clearly labeled. And that concludes 10-1, 10-2, and 10-3. Okay, make sure you come to class with questions, and I will see you on Tuesday. The wrap up on 10-2. That last slide is basically what we just did. So we're all set. So that was 10-2.